Hello everyone. My name is Malik Arslan Nisar, and I am a PhD student in the Department of Mechanical Engineering at IIT Kanpur. And I am the course tutor for this course, 4-week course, Principles of Vibration Control. So I welcome you to the first session of this first recorded session. So basically, I have already taken the live session, but there was some technical issue due to which the recording was not visible. The screen was blank basically. So I am again recording the session, but this time it would be without the learners. So kind of a recorded session, you can say. And since I'm re-recording this session, it would be of significantly shorter duration than the live session. So I think without any delay I shall get started now. Yeah, so I hope my screen is visible. Yeah. Okay, so as you can see that this questions are already solved because it was from the live session. But I will go through each of the questions again. Okay, I will explain the solutions again. I will not solve them completely here because the solution was already done in the live session. So I'll just read through the solutions and explain what it means. So the first question you see here is that the balancing of inertia forces can be classified as the following method of vibration control. So first of all, system modification, active feedback control, excitation reduction at source, and energy harvesting. So we had studied in lectures also in detail that there are various ways of vibration control. Okay, some of them include passive techniques, some of them include active vibration control. Okay, and some of them include that you are making some modification in the system itself, for example changing the mass or stiffness of the system or the damping of the system, or maybe you're using an isolator to separate the system from the disturbance. So there are various methods. Now here it is asking that balancing of inertia forces falls into which category. Since balancing of inertia forces means that we are basically at the source itself, we are basically adding or adding some weights or trying to change the vibration there itself, because inertia forces, they are basically at the source itself. So this falls into the excitation reduction at source. Why not the other? Because in system modification, as I said, that our primary system, we are making changes to that. So here we are not doing any sort of that thing, neither we are taking any active feedback control from the system. It is not active feedback control. And in case of energy harvesting, what we do is that the vibration at the system, we are trying to use that vibration energy. Basically we harvest that vibration energy, we dissipate it and use it for some different purpose. So balancing of inertia forces is basically excitation reduction at the source. Now coming to the second question, a single degree of freedom system having stiffness of 625 Newton per meter and mass 1 kg is subjected to an excitation of 0.1 Hertz. Which parameter modification will be important for vibration control? Okay, so before we jump into this, you have already seen in the lectures as well that there are different regimes, okay, where different system parameter is important for vibration control. Okay, so the complete uh, derivation was there, so I will go through it again. So for example, we are assuming that our force is, okay, sorry for that. um, yeah, okay, so our force, which is of harmonic nature, is F sine omega t, and corresponding to that we have a displacement x equal to x sine omega t, since this is a single degree of freedom system. Now our velocity would be x omega cos omega t. Okay, it is simple, basically simple differentiation. And wait a minute, let me change this to, okay, there is no option for pointer here. Okay, here it is. Okay, yeah. And similarly our x double dot will be minus x omega square sine omega t. Now according to the Newton's third law, we know that the summation of forces should be equal to the mx double dot. So here, since there is only stiffness has been mentioned and mass, so we will not consider a damper. So our system is with a spring, with a spring mass system basically. So you can see that uh, we can draw the free body diagram of this mass with F sine omega t acting in the right direction, and the spring force acting in the opposite direction, which is shown here as kx. So we will assume that the right side is positive x. So when we write the equation, we can write it as minus kx plus F sine omega t is equal to mx double dot. I hope this is clear. Now we can put the values of x and x double dot from here. Okay, so it would be minus kx sine omega t plus F sine omega t is equal to m m into minus x omega square sine omega t. So the sine omega t will get cancelled from each term, and the final equation we get is f equals to minus m omega square x plus sine x. So remember here, this capital X represents the amplitude, while the small x represents the response of the system. Okay, so you can denote it by A or B, like any other letter also. I am using capital X. So here you can see that f is equal to k minus m omega square x, and you can by simplifying you can write it as x is equal to f upon k by 1 minus m omega square k. Now omega has been given in the question, so we have been given as a excitation frequency f as 0.1, so we can simply write omega equals 2 pi f, and from here we can find out the omega. Okay, now uh, yeah, so now you can see here that you can further simplify this thing, because you know that the uh, omega, which is basically the non-dimensional frequency ratio, okay, which is the excitation frequency upon the natural frequency of the system. So you can write it as omega upon under root of k by m, which is omega square upon k by m. Like if you're squaring this whole term, so it will become omega square here. Now if you see here, it is nothing but this omega square. Okay, so let me just write it here. It should be implies this is equal to omega square. Okay, yeah, so you're putting this in a more simpler form, which is x is equal to f upon k upon 1 minus omega square. Now we can just find this omega, which is equal to 2 pi f, which is the basically the excitation frequency, which is 2 pi into 0.1 upon the natural frequency, which is under root of k upon m. The values of k and m are already provided. So So this comes out to be something like 0.02513. Okay, and if you substitute it here, you can see that 1 minus omega square. Since this omega is very less, omega square will be much lesser, so it is approximately equal to 1 only. So you can see that this x is equal to f upon k. So here only stiffness parameter remains. So for this system which we have been given, the important parameter for the controlling the vibrations is basically stiffness. Okay, now you can also remember from the lectures that there was this transfer function versus omega graph which was shown. Okay, transfer function, here we are using the displacement. Okay, so the graph is something like this, and the different regions of the graph, okay, you can you don't have to memorize it, but you can simply remember it, that this omega, when it's very less than 1, it is stiffness. The whole derivation has also been shown. So for here I have just done it for the stiffness parameter. So when this omega is very less than 1, for example here it was 0.025, then the parameter which is important for vibration control is stiffness. And if this omega is equal to 1, the parameter important for vibration control is damping, which you can also see here corresponding to this peak. Okay, so here the value of omega, which is basically the ratio of natural excitation frequency upon natural frequency. And if this omega is much greater than 1, then this is mass or inertia control. So basically in this graph you can remember simply that this region corresponds to the damping control. Beyond this it is inertia control, and before this it is stiffness control. Okay, so I hope this is clear. Now moving to next question. So it has been asked that why are baffle walls used in the propellant tank of a rocket engine? So as you can see here that we have the propellant tank, okay, basically which stores the fuel like this, and inside this we create baffle walls. Basically these are metallic you can say strips kind of inside the propellant tank. Okay, so why is it used? First, it is for reducing stress concentration, for preventing sloshing of fluid, for corrosion prevention, for vibration isolation. So basically in case of these propellant tanks, there is a lot of fuel, and while during the motion this fuel basically moves very from like this direction to this direction. Okay, and it causes the sloshing of fluid, which can also lead to the shift in the center of mass of the system, and which will not be a good thing obviously, because if the center of mass of the system shifts, this can topple. Okay, and we do not want that thing. So and that happens because large waves are created if there are no baffle walls. So we just introduce these baffle walls so that the whole fuel is broken into small sections, so larger waves are not created. So there is nothing such as corrosion prevention which we are getting out of these baffle walls. Neither they help in the reduction of the stress concentration, and neither they are used for vibration isolation. Okay, so the main purpose of these baffle walls is preventing the sloshing of the fluid. Okay, I hope this is clear. Now moving to the next question. So here we have the Strouhal number of a pipe obstructing a river flow is 0.2. The free stream velocity, the free stream flow velocity is 2 meter per second, and the radius of the pipe is 0.5 meter. The vortex shedding frequency is. Okay, so first of all we can just like try to understand what this vortex shedding frequency is. So basically, whenever there is a flow basically of a fluid, and if we put something in its path, for example, I'm putting this cylinder sort of thing, okay, or a circular thing, a cylindrical thing, anything we can put. So in this case the flow will be obstructed, right? So what happens is that this uh, these the flow is interrupted, and there is the formation of this basically what you can say, these are known as vortices, okay. So basically there is a sort of opposite alternating force created on this side, on the basically the top and bottom, because of the this flow which has been obstructed, okay. Now the vortex shedding frequency is that the amount of vortices which are created in like per second, okay. Now you can see that this vortex shedding frequency, it will be directly proportional to the flow velocity, which is very intuitive, because if the flow is larger, it means that every second greater number of vortices are shedded or created. Shedded basically means the moment of these vortices per second, okay. So that is the vortex shedding. And you can see that if the this frequency is inversely proportional to the diameter, because if the diameter is larger, so the flow will not be interrupted that much, and you can see that, no, sorry, basically if the diameter is larger, this uh, force will not be that, these vortex formation will not be that much, so it is inversely proportional to the diameter. So from here we arrive at that frequency is directly proportional to V and inversely proportional to D. And so when we change this proportionality into basically equality, we get this constant which is known as Struwell number. Okay, so here also what we are being asked is the vortex shedding frequency when the Struwell number is given, the stream flow velocity is given, and the diameter, basically radius of the pipe, is given. So we plug in these values, which is 0.2 into 2 upon the diameter, which is 1, twice of the radius. So we get the frequency as 0.4 hertz. So that is the correct answer. And I hope this is clear. Now coming to the next question. A moment. Sorry for the interruptions. I have not been well since past week, which is also why there is a delay in the recording. So okay, now yeah, coming to the fifth question. Detuning is referred as the process of changing the loss factor of a vibrating system, changing the nature of frequency band, changing power spectral density, and changing the stiffness and inertia of system. So we have seen that detuning is basically the process of changing stiffness and inertia of a system. Basically we are trying to take the natural frequency uh, of the system away from the excitation frequency. So that is why we are changing the stiffness and inertia parameters, because that is what governs the natural frequency of the system. Now I think uh, Okay, basically here I have just explained that what this loss factor means here. So loss factor is the energy dissipated per cycle per radian upon the maximum strain energy in the system. So if we try to figure it out, so it is where we can say D is the energy dissipated per cycle, and uh, per radian, so we divide it by 2 pi upon the maximum strain energy. So maximum strain energy we have here is half of k a square, where a refers to the amplitude. So you can see that this loss factor comes out to be c upon omega k, which by simple modifications, like you can uh, simplify it to 2 zeta omega also. Okay, so basically here I think I have just, yeah, here you can see, using these relations you can simplify this c omega k to 2 zeta omega. Okay, so this is basically the loss factor. And like changing the loss factor of a vibrating system is not detuning, because you can see that it does not depend like it cannot control the natural frequency of the system. Okay, so detuning is basically changing the natural frequency of the system, which can be done by changing the stiffness and inertia, because it depends on k and m. Okay, now moving ahead, which of the following statements is false? Displacement amplitude near resonance condition is primarily controlled by damping. Okay, we have also seen this graph before, that the you can also derive it in the similar way I did it for stiffness. Okay, so you can put when there is near resonance condition, so basically the omega will the frequency ratio will become 1. So you can solve this analytically also, basically for all the cases. So I will simply show it in graph, because I have done the one case for you. You can try it out as well. So you can see that, yeah, near the resonance condition the displacement amplitude is controlled by damping. So this is correct option. Second is, the damping is the only effective means for controlling the vibration, which is incorrect, because we have seen that we can basically control the stiffness parameter or the mass inertia parameters, or even we can try to isolate the system. So there are various methods of effectively controlling the vibration, not just damping. So this statement is false. Okay, the third statement is, there are different controlling parameters in different frequency range, which is correct, which we have seen that here also, that in different frequency ranges we have different controlling parameters for vibration. And Tacoma Narrows Bridge failed by aeroelastic flutter. So yeah, the phenomena was simplified to that the resonance condition, the incoming the wind waves that time, they were almost close to the natural frequency of the bridge, so which causes causes the basically the the resonance condition, and the in fact the phenomena was much more complex, um, but that condition, the resonance condition, caused aeroelastic flutter inside the bridge, which ultimately led to its failure. Okay, now moving on to the next question, we have, which of the following statement is false? Energy dissipation per cycle in viscous damping is given by the area of ellipse. Okay, so we have derived this here, that in case of viscous damping, we know that we have a piston and cylinder arrangement, where we have viscous fluid inside this cavity. So when we try to move this piston with a velocity x dot, so the force which opposes its motion is known as the damping force, which is given by Fd equal to Cx dot. So basically that damping force is proportional to the velocity of this piston. Okay, so here also you can say that the x can be like a harmonic profile displacement, which is x sine omega t, and similarly we can get x dot, which is x omega cos omega t. X double dot is minus x omega square sine omega t. Now since we are talking about energy dissipation per cycle, so let's just calculate that. The energy dissipation per cycle is nothing but equal to, we know that we simply write the energy dissipation as f dot dx, right? The work done ultimately, which is f dot dx, and here also we are basically multiplying and dividing by basically dt, or in other terms you can say that we know that power is f dot v, and power into dt will give us the energy dissipation. Okay, so this is just a class 12 level formula. Okay, so here now we can put this fd from here, which is cx dot. Okay, now c is like this, and x dot you can put from here, which is x omega cos omega t. Okay, so it becomes yeah, fd is cx dot. Okay, so you're writing that. Then we have dx upon dt, which is again x dot, so basically it is cx dot square, so that is why you have squared this whole term. So it's cx square omega square cos square omega t into this dt. Now it's from 0 to time period t, which here is 2 pi upon omega. And if you see that we try to simplify this. Okay, this here I have multiplied and divided by 2. You'll come to know why. Now this cx square omega square upon 2, this you can directly take outside because it's constant. Now this 2 cos square omega t, you know that this t cos square omega t can be written as 1 plus cos 2 omega t. Okay, simple trigonometric formula. So when you simplify this, okay, I'm not going to elaborate this here because it's just algebra, like you can solve it. So ultimately when you integrate, it comes out to be d is equal to cx square omega into pi. Okay, now yeah, so what our question was here is that okay, is given by the area of ellipse. Okay, so this is the energy dissipated. Okay, it was basically just for making the students understand at that time. Otherwise you can simply write it as fd is equal to cx dot x is equal to x sine omega t. Okay, now here by making simple modification, you can write fd is upon cx omega is equal to cos omega t, and this x of t, which is basically the response, upon amplitude is equal to sine omega t. Now cos square omega t plus sine square omega t is equal to 1. So this will be our right hand side, and on the left hand side we have fd upon cx omega square plus x upon x square, which is basically the equation of an ellipse, right? And if you see, if you draw this ellipse, it's this major axis will be this capital X, and this minor axis will be this cx omega. Okay, you can draw it for yourself. So this area represents this cx square omega into pi. Okay, so the energy dissipated per cycle in viscous damping is given by the area of ellipse, so this is the correct option. Now the second one is energy dissipation per cycle in Coulomb damping is given by area of rectangle. Okay, okay, sorry. Okay, give me a moment. So yeah, for the Coulomb damping, we know that uh, the Coulomb damping, or basically the friction damping, here we have, for example, these two surfaces which are trying to move against each other, so there will be a sort of friction, and you can say that, for example, this is their mean position, and uh, from this mean position, say 0, okay, this friction force is given by Fs, which is a constant force, into signum of x dot. So basically signum of x dot gives the sign of the velocity of the basically the sign of the velocity. So here you can see that as it tries to move from this point 0 to point A, okay, here the uh, first the frictional force will be basically Fs, okay, and then it will remain constant till the point A. Now when it changes the direction, okay, it tries to come downwards, so you can see that the value will again remain Fs, but the direction will be negative, it will be reversed. So from here it will directly jump to this point, okay. Now see, the position is x, okay, so the position is x, but the force has changed its direction to negative Fs, okay. Now as it moves from this point to this point, the direction and the value of the force remains same, which is negative, but the x is basically changing from x to 0. So this is how it goes till here, okay. Now at this point again, the force is obviously, because the direction is same, so the force is negative, and the x is basically, this side we are assuming positive x, the x is going to be negative, so this x is also turning out to be negative till point this, okay. Now here what happens, it was in this direction, now again the direction is going to change, okay. So as the direction changes, the x is still negative, but the force becomes positive, the direction of force becomes positive. So x is still negative, but the direction of force becomes positive, so we reach to point here. And now as it moves to 0, the direction of force is the same, which is positive, but the x is going to be basically the negative x is decreasing from minus x to 0. So this is how this is formed. So you can see that, yeah, the force done is basically, we know that F and X, the area under the Fx graph gives us the work done, which is integration of f dx. So this is a rectangle. So yeah, the energy dissipation per cycle in Coulomb damping is given by area of the rectangle. Now energy dissipation per cycle in hysteretic damping is dependent on frequency. The energy dissipation per cycle in hysteretic damping is independent of frequency, okay. So yeah, so for that you have to see that, see, in case of hysteretic damping, we are replacing the viscoelastic damping model, and here the damping coefficient changes up by h upon omega. Now here when we figure out what the damping, basically the energy dissipation is, it equals to pi h x square, or 2 pi eta into u max, okay. So here you can see that this thing is not dependent upon the frequency, so the hysteretic damping is not dependent upon the frequency, okay. So now wait a minute. Okay, so I have corrected my AirPods, so I think now the sound should be better. Okay, so coming to the eighth question, which of the following methods are useful for controlling vortex induced vibrations? So We have just discussed what the vortex induced vibrations are. So installing helical spoiler around tall cylindrical structures, streamline construction of the marine pier, woven plastic ribbon into marine cables. So all of the above options are correct, because installing in the tall cylindrical structures like tall buildings, we are introducing the helical spoilers in order to basically disrupt the formation of vortices, so which results in obviously less vortex induced vibrations. Similarly, as you can see here, I have shown that in case of streamline construction of the marine piers, the flow of the liquid is not obstructed much, you can see, due to the streamline shape. So these vortex or vortices formation is also less because of that. So this is also a correct option. And similarly, in case of the just like the helical spoilers are used for tall cylindrical structures, similarly in case of marine applications, we are using woven plastic ribbons onto the marine cables, so that in the water, this in the similar way, the vortex formation is basically obstructed. The formation of vortices is reduced. So all of these options are correct. Now coming to the ninth question, which of the following is false with respect to detuning? So we have seen that detuning is the process of changing the stiffness and inertia parameters of the system, so as to basically change the natural frequency of the system, and make the natural frequency of system go away from the excitation frequency or any sort of external force frequency, etc. We want to basically take it away from that. So the first option is technique of changing system parameters to avoid resonance, which we mentioned that yes, we are changing the stiffness and inertia parameters so that the resonance condition is not met. So this option is true. Second option is detuning shifts the natural frequency towards excitation frequency. So it is not correct, because it shifts the natural frequency away from the excitation frequency, which is basically our purpose. So this option is false. Now the third option is stock bridge damper is used for detuning in overhead power transmission cables, which is also correct, that we are using the stock bridge damper in case of transmission cables for detuning purposes. So option 2 is the only incorrect option here. So that would be our correct option for this question. I hope that is clear. Now moving to the final question of this session. So in a viscous damping model, displacement is equal to 10 mm. The damping coefficient is given as 7 Newton second per meter, and the excitation frequency is 100 radians per second. So find out the energy dissipated. Okay, it is very simple. We have seen the formula for this one. In fact, we have derived in question 7, I guess. So for a viscous damper, we know that the energy dissipated, which we calculated, was coming out to be pi c omega x square, where x is the amplitude of vibration, which is given as 10 mm, which is equal to 0.01 meter. We have to put everything in SI unit. And the value of c and omega is given as well. So omega is 100 radians per second only. So when you put these values, okay, into the formula for energy dissipation, you can check for yourself that the answer is coming out to be 0.22 joules. So this is the option 1 given in the question. So that should be our correct option. So this was about the first lecture. Now since it is a as I mentioned earlier also, it is a pre-recorded lecture, so the duration is significantly shorter, but I hope everything is clear as we have discussed in the live session also. If there are any doubts, you can ask me in the upcoming live session. And so by saying that, I'll end today's lecture here only. So thank you very much, and I'll see you in the next one.